Yeah, hello and welcome back to the discussion on AVL trees. In the previous videos, we have seen that AVL trees are balanced binary search trees, which supports insert, delete, and search operations in order log. And in this video, we are going to see some more applications of AVL trees. In other words, in addition to insert, delete, and search, we'll try to do more operations. So one such operation that we're going to discuss is the first one that we're going to discuss is the uh, rank of x. So rank of x is defined as 1 plus the number of elements which are greater than x, right? So the application is that we have a dynamic data set. Dynamic in the sense that the elements are added and deleted, and we need to also support search. And in addition to that, we also want to know, given an x, the rank of x is the number of elements which are bigger than x in this collection, right? So as the set changes, rank of a particular number will keep changing. So at any some point of time, among all the numbers which are there in the collection, we want to find the rank of x. So in order to answer this question, so we will use the AVL tree implementation. In addition to the other structures, other parameters that we had, we will have one more variable in each node of the binary search node, which is called as count. The count will tell you the number of nodes in the subtree rooted at this node. I'll repeat. The count of a node is the number of nodes in the subtree rooted at this node, right? So if you go to the root node, so I have written 11 here. So 11 is the total number of nodes in in the entire tree. So if we go to the right hand side, the number of nodes in the subtree is 4. So this will have 4. So when you have come to 93, the number of nodes in the subtree is 2. When I go to the other side, the number of nodes in this subtree is 6. The number of nodes here is 3. Okay, so this, how do you update the this count? This count is updated by, so if you want to update it from bottom up approach, it's easy to upload. So all the leaf nodes will have 1 because it doesn't have any child. The number of nodes which are there in the subtree rooted there is 1. And when you go to a parent node, so this the count for this is the count on the left child plus the count on the right child plus 1. So the number of nodes here is, so this node plus the number of nodes on the left hand side, which is given by the count on the left side, plus 3, which is the number of nodes on the right hand side. So once I have, so if you're computing the count from bottom up, it's always easy to update this. So when you insert a node, so if you're planning to insert a node in this subtree, let's say that I want to insert a node which is 40. So what I do is that I start searching for 40, which is not there in the collection. I'm going to insert here. But when you start inserting the node itself, you know that this node will be inserted in this subtree. So as and when you go along this path, you increase the count by 1. So when you want to insert 40, so this becomes 11. I come here, this node becomes 7. When I come here, it becomes 4. When I come here, it becomes 2, and I insert here and add 1 more. In other words, when you are searching to add a number which is not there in the collection, add along the path plus 1 till you reach the node, and when you create a node, add 1 to this. Similarly, when you want to delete, so if you want to delete 39, then what you do is that you start searching for the tree. So you start, when you delete a node in this subtree, you know for sure that one node is going to go. So decrement the counter by 1. Since 39 is smaller than 52, I go to the left. Since I come here and I know that I'm going to delete a node in this subtree, I'll decrease the count by 1. Then I come here. I know that I'm going to delete a node in the subtree, so I'll make this as 2. I come to this node and delete it. So when you delete, there are 3 cases. In the case 2, you're only going to replace the number of nodes in the subtree along the path will keep continuing. When you find the inner traversal again along this path, you're going to decrease. And once you delete the node, anything below that, the number of nodes will not change. So let's quickly look at how to compute these. So what I'm saying is that the structure of the tree will have, in addition to the key, you have an additional pointer to be maintained, which is the count, right? So the count pointer is what we are going to maintain, which is the additional count here. Height is required to verify the height property. Then you certainly need the left and right pointer, but you have the option of keeping the right pointer, and the balance binary search tree is based on this. So how do you compute the count of a node? If you want to update the count of a node, so this is during when you do the rotation. So after you do the rotation, we updated the height of x, y, and z. So the count of x, y, z also will change because of the rotation. So when you go up, when you after you deleted a node or inserted a node, we need to keep track of the counts when you do the rotation. So the count function, given a node, it will update the count function. The count function is defined simple. So if the node is null, the count for that is 0. If node has both the children, then the count of that node will be 1 plus the count on the left hand side plus the count on the right hand side. If one of the child is null, if the right child is null, then the count for that node is 1 plus the number of nodes on the left hand side. If the right child is not null, then it will be 1 plus the number of nodes on the right hand side. So if both the pointers are null, then it's a leaf node, so the count for that will be 1. So once you delete and when you so search will not change the count. So when you insert a node, count of several nodes will increase. When you follow the path to find the node to delete, you increase the counts. Similarly, when you find the path to delete a node, you decrease the counts by 1. After you do the rotation, you keep going up, updating the height. When you do the rotation, uh, after you do the rotation, after you update the height, you have to update the count of the nodes x, y, and z. That's why you're going to call this function and update the values of x, y, and z. So once you know how to compute this number, the count of a node is the number of nodes in the subtree rooted there. This can be used to find the rank of a node. So before I come to the rank of the node, so this count also will solve one more problem. So we wanted to discuss how to deal with the duplicate numbers. So if the duplicate numbers needs to be even considered, suppose I want to add one more 32, right? So what I do is that when I want to add one more 32, our search algorithm starts with 52. So when you go along, start searching for 32, you increment the counters by 1. This becomes 12, this becomes 6, 6 becomes 7. When I come here, this becomes 4. Since I found a node there, I just stop there. I don't insert anything. I don't maintain any other additional information. So if I want to add one more 32, I again start, this becomes 13, this becomes 8, and this becomes 5. So how do I know how many 32s are there? So how many nodes, what is the frequency of a key value at a node is given by the count of this node minus the count on the left side minus the count on the right side. So if you want to delete 132, again the same algorithm, you start searching for it, decrease the counts by 1 till here. If it is still positive, you don't delete this node. If it becomes 0, then it's not a node in the valid tree, so only in that case you delete. So once you maintain this count property, so you can allow duplicate keys in the binary search tree. But every key, there will be only one node. This count will keep track of how many such nodes are there. Okay, I repeat that the frequency of a key value in the node is equal to count value of that node minus the count of value of the left child minus the count value of the right child. So you delete a node only when this count is turned to 0. Otherwise, every time when you increase, when you want to insert, when you search for all the nodes till they reach this node, count value of all the ancestors of the node will increase by 1. And when you start deleting a node, when you start searching for this node, decrease the values by 1, right? So this is a nice way to handle the duplicate entries. So let's come back to the question of how to find the rank. Let's look at, I'll take an example. So let's say that I want to find the rank of 39, right? So from this example, you can see that 39 rank is 7 because so there are five nodes. Rank of 37, 39 is 6 because there are five nodes which are bigger than 39. So those nodes are 82, 95, 93, 64, 73, and 52. Okay. So rank of 39 is 6. So if I give you 39, how will I find the rank? I start at this particular node. So what will be the rank of 52? The rank of 52 is 6, 5. How do I know? So all the numbers which are bigger than this are on the right hand side. So if you just look at the count on the right side, this is 4. That means that in this subtree, there are exactly 4 numbers which are greater than 52. So the rank of 52 is actually 5, 1 plus the number of nodes which are bigger than this. But I am interested in finding the rank of 39. So I compare with 52 with 39. So 39 is on the left hand side. I have to go to the left hand side. So when I go to the left hand side, I am ignoring several numbers which are all uh, bigger than the bigger than 39. So I am ignoring the number 52 since I am going to the left. So whatever node that I'm going to from where I'm going to the left, this is also greater than 39, and all the numbers on the right subtree are also greater than 39. So and I don't have to go and search how many numbers are there. The right child will tell me the number of nodes which are greater than 52. So when I come to 39, so I already know that the number of nodes which are greater than 39 is 5. I'll keep track of the count 5. So now 39 is bigger than 26, so I take a right turn. So when I take a right turn, so the 26 is smaller than 39. That's why I took a right turn. But 26 I'm going to ignore because this will not contribute to the rank of 39. So only the numbers which are bigger than 39 will contribute to the rank of 39. This 26 will not contribute. And the numbers on the left hand side are all smaller than this number. So this obviously will be smaller than 39. So I'm going to ignore everything. So now when I reach 32, I have again I compare. I go to the right side. When I go to the right side, I'm going to ignore 32 and 29. So I reach this node. The count that I'm remembering is 5. And when I reach this node, I see if it has the right child. If it has the right child, then I have to, all these numbers also is going to be greater than 39. I have to add this count to the number of nodes on the right subtree to the count that I have. In this case, there's no right child. So the number of nodes which are greater than 39 in this subtree is 0. So the total count that I have seen is 4 plus 1, which is 5, which indicates that the number of nodes in this tree which are greater than 39 is 5. So the rank of 39 is 6. So the algorithm is simple. So I have a count to remember, um, and I start searching for this node for whose rank I want to find. And when so the search basically is either I go to the left or I go to the right. So in case if I go to the right, I ignore all the numbers on the left hand side. That means that I am going to ignore all the numbers which are smaller than x. I don't have to keep track of any of them because none of them contribute to the rank of x. But if I take a left turn, so the numbers on the right hand side all will be greater than x, and the number from where I came from also will be greater than x. That's why I'm going to the left. So I have to increment my count by 1 plus the number of nodes on the right hand side. Right? Just repeat this process till you reach the node that is there, or you reach the point, reach a null pointer. Let's quickly look at the code for this. So the code for this will look something like this. So I want to find the rank of x in the binary search tree node. So I start with a rank as 1 because this will ensure that rank of a node is 1 plus the number of numbers which are greater than this. So if I find this node, so what I do is that I'll update my rank to be the number of nodes on the right hand side plus the rank. Rank is updated as rank plus the number of nodes on the right hand side, and then return this rank. Right. So this is what will be my rank. If the x is smaller than the node key, that means that I'm going to go to the left hand side. When I go to the left hand side, so I do +1. This is to ignore the node, the present node, so which is greater than x, right? X itself is greater than x, so this node will contribute to one rank. And I look at the right child. If the right child is not null, then I add all that to the rank that I have, because all of them are greater than x, so all of them will contribute to the rank. On the other way around, if I take a left turn, so if I update my, if the number is small, if the node value is greater than smaller than x, right? So that means that the number that I'm searching for is greater than the node value, then I go to the right hand side. So when I go to the right hand side, I'm ignoring all the numbers which are smaller than x, which don't contribute to the rank, so I don't update my rank. So at the end of this while loop, whatever is the value of rank, just return that rank. Since the height of the tree is log n, so every time you're going down by one level, so the complexity of finding the rank is order log n. So once you know how to find rank of x, the next problem that I want to ask is, so given a rank, find a number such that the rank of that is x. Okay, let's go back to the tree that I have. I want you to give me a node whose rank is 6. Okay, so earlier we have seen that 39 is the node whose rank is 6, but I'll give you 6 now. So once I give you 6, you have to give me the pointer to this node, right? That's the problem. It's the reverse. So I give you a rank. The rank that I'm going to give you is between 1 and n, where n is the number of nodes. The rank 1 number is the maximum number. Rank n is the smallest number, right? So I give you 6. I should end up in 39, right? Let's start with the root node. So can you tell me what is the rank of 52? We know that the rank of 52 is 5, because only the numbers on the right hand side are greater than 52, and we know that exactly there are 4 numbers which are greater than 52. So the rank of 52 is 5, but I am looking for a number whose rank is 6. So the rank of the number that I'm looking at is bigger than the rank of the root. So that number that I am looking for should be there on the left subtree of the this tree, right? So let me repeat. If I am looking for a number whose rank is 6, but the rank of the root node is 5. So the rank 6 should be smaller than 52. So I come to the left hand side. So when I come to the left hand side, so I'm ignoring 5 numbers which are bigger than 6. So I will remember that when I go to the left, 6 was the original rank that I have to find in the entire subtree. But I have ignored 5 numbers which are bigger numbers now, right? So because I went to the left. So in this subtree, right, in the left subtree, I want to find an element whose rank is 1. So I want to find an element whose rank is 1, but the rank of 26 is 3 plus 1, which is 4. So I am looking for a rank which is 1, so which will be on the right hand side. So I go to the right side, right? So if I'm looking for a rank which is smaller than the rank of the node, I should go to the right. If I'm looking for a node whose rank is bigger than the rank of the root node, so I'll go to the left, right? So this node has rank 4, but I'm looking for a node whose rank is 1, so I decide to go to left hand side. So the rank of this node is 2. How do I know the rank of this? Just go to the right child and look at how many nodes are there, plus 1. In this subtree, among the numbers in this subtree, the rank of 32 is 2. So, but I am in this subtree, I am looking at a number whose rank is 1. So, which is again smaller, so I come to this node. So when I come to this node, the rank of this is 1, because it doesn't have a right child, right? So in this subtree, the rank of this is 1. So I was looking for a number whose rank is 1. I stop and report 39. Let's look at, I want to find an element whose rank is, let's say is 4. Okay. So I start here. I want to look for a number whose rank is 4. The rank of 52 is 5. So what we should do is I should go to the right because I am looking for a rank which is smaller than the root of rank of the root. So when I take a right turn, I'm ignoring all the numbers. Don't worry about it. So I go to 73. I'm looking for a number whose rank is 4, but the rank of this is 3, right? So because on the right hand side there are two numbers, and in this subtree, this is the only numbers which are greater than 73. So the rank of 73 is 3, but I am looking for a number whose rank is 4. So I should go to the left. So when I go to the left in this subtree, I should look for a number whose rank is 4 minus 3. 4 is the rank that I wanted to originally look at. But when I came here, I ignored three numbers which are bigger than this. So when I go to the left hand side, I should look for a number whose rank is 4 minus 3. So I come here. So I try to look at the right child. The rank of this is 0 because rank of this is 1 because the right child has zero number of children. So the rank of this is exactly 1. So when I start here at the 52, I was looking for a number whose rank is 4. When I came here, I am looking for a number whose rank is 4, but the rank of this node is 3. So the smaller rank should be on the left hand. Rank of this is 3, so I want to look for a number whose rank is 4. So this has to be a smaller number. I come here, but when I come here, I am looking for a number whose rank is 3. 4 minus 3, which is 1. So when I come here in the subtree, there is no right child, so the rank of this is 1. I stop. Let's write the code for this. This is also easy. So I am given rank here, right? So R is a variable that I'm going to keep track of. So if the node is null, or the rank should be the node should be not null, rank should be greater than 0, and it should be smaller than the count plus 1, right? So it should be smaller than the count plus 1. It can be equal to the count. So in other words, the rank of a number should be between 1 and n, where n is the number of nodes in the binary search tree. If these conditions are violated, then I'm looking for something which doesn't exist in this binary search tree. So I'll end up returning 2. So you should have a valid pointer. The rank of the number that I'm looking for should be between 0 and the number of nodes in the subtree. As long as this is true, then if the right child is null, not if the right child is not null, then I check how many nodes are there in the right side, right? So the number of numbers on the right hand side is um, um, node right count plus 1. This plus 1 is including the node that I'm presently in, right? And if the right child is 0, if the right child is null, then my R value is 1. In other words, when I'm at this node, I'm trying to find the rank of the this particular node in the subtree. Rank of this particular node is exactly equal to 1 plus the number of number of nodes in the right side. So if the right side is empty, then the rank of this node is going to be 1. Otherwise, it will be 1 plus the number of nodes on the right subtree. So I found the rank of the node. If the rank of the node, that is R, is equal to the rank that I am looking for, right? So I want an element whose rank is rank, but the rank of the node that the root node is R. So I found this node, so I just return this. If the rank that I'm looking for is greater than R, right? So the rank that I'm looking for is greater than the rank of the root, right? So when I come to the node in this subtree, the rank of this node will be 1 plus the number of nodes on the right subtree, right? So the rank of a number is defined as 1 plus the number of nodes on the right subtree. If I go to a node among all the numbers in this subtree, how many numbers will be there which is greater than this is exactly equal to the number of nodes on the right subtree. The small r that I have written here is the rank of this node. But the rank that I'm looking for is greater than the rank of this node, right? That means that what I'm looking for is in the left subtree. I go to the left subtree, but I have to ignore R numbers, right? So R is the number of numbers which are all greater than the rank. So when I go to the left subtree, I'm ignoring R numbers. So which are the R numbers? The one is the node that I'm presently in, and all the numbers on the right subtree. So and recursively find in the left subtree an element whose rank is rank minus R. If the rank that I'm looking at is smaller than R, that means that rank that I'm looking at is smaller than the rank of the root node, then the rank, that node that I'm looking for will be on the right hand side. When you go to the right hand side, you don't have to change the rank number. So because you're ignoring the numbers which are all smaller, so if you're ignoring numbers which are all smaller, they don't contribute to the rank. So when you go to the right, you don't make any changes. So when you go to the left hand side, you're ignoring a lot of numbers whose rank is lot of numbers which are greater than the present node. So you have to account for that by subtracting the number of nodes which are greater than this. The number of nodes which are greater than this is the number of nodes which are on the right hand side plus the present node, right? So this algorithm will give you the node whose rank is exactly equal to R. Again, this will run in order log n because the complexity of this algorithm is exactly same as the search, because at every comparison you either terminate or you go to the left side or right side. So the number of comparisons done by this algorithm is exactly equal to the height of the tree, which is log n. So now once you find the, once you know how to find the rank, then the range count is easy to answer. So what is the range count? So I give you two pointers, L and R. I want to know how many nodes are there in this binary search tree whose values are between L and R. So this is easy to compute in this case because I know how to find the rank. So I find the rank of L, right? So rank of L will look at all the numbers which are greater than R, right? So I want, so this is your L, this is your R. So the rank of X will, L tell me all the numbers which are greater than X. Rank of R will tell me all the numbers which are greater than that. So if I subtract then rank of L minus the rank of R, then so this will give me the number of numbers which are between L and R, right? So when I compute the rank of L, so this is the number of numbers which are strictly greater than L. So L will not be included, right? So here also, if R is there in the tree, in the rank of R, it will not be included, but R will be included in rank of L. So when you do the subtraction, R will be there, but L will not be there, right? So when I do the range count, we are assuming that L and R, if they are there in the binary search tree, both can be included, right? So the number of numbers greater than or equal to L, but smaller than or equal to R is what I'm looking for. So this will not include L, but will include R. So in order to take care of L, I just do a search for L. If L is there, I increment the count by 1. Otherwise, I'll not increment the count by 1 and then return the count. So this function will compute the number of nodes in the binary search tree which are greater than or equal to L but smaller than or equal to R. So the note that the earlier algorithm that we had written for the range count dependent on the number of nodes. Right here, it's independent of the number of nodes because you have to just compute the rank twice, and both the ranks can be found in order log n. So the complexity, and then do one search. This is clearly order log n. So this range count will only depend on the height of the tree. It is independent of the number of nodes in the subtree. With these ideas, we can do a few more things, similar things. Let's say that I want to compute the prefix sum of x. So what's the prefix sum of x? So among all the numbers which are there in the collection, I want to find the sum of all the numbers which are smaller than x, right? Smaller than or equal to x, right? So how do you find this? We have to augment, we have to add one more variable into the structure of the binary search tree called the sum. So this sum will keep track of the this sum will is the sum of all the key values in the subtree rooted at this node. How is it defined? This is defined as the value of this node plus the sum of numbers on the left hand side plus the sum of numbers on the right hand side. So when you insert a node, when you start searching for the node, you increment the sum of every node by the node that you are incrementing. When you delete a node, you decrement the sum of every node along the path by the um, value of the key that you are going to delete. So once you do these two changes, then when you do the rotations, after you do insert and delete, when you do the rotations, after you do the rotations, the sum of x, y, z needs to be computed. So for that, you can write a sum function which will compute the sum. So this is exactly similar to the count function, right? The count function was 1 plus the count on the left hand side plus the count on the right hand side. Here the sum will be value of the key plus the count and the sum on the left hand side plus the sum on the right hand side. So just by adding one more variable to the binary size structure and making appropriate changes during the add and delete and rotation, you can compute the prefix sum in order log n. So I want all of you to figure out the code for this. This is just adding a few more lines to whatever code that we have. So once we know how to find the prefix sum, then I can find what is known as the range sum. Range sum is I give you two numbers. I want you to find the sum of all the numbers which are between x and y, right? So once you know the prefix sum, this is basically equal to prefix sum till y minus the prefix sum till x, right? So the range sum of x comma y can be computed using the prefix sum y minus prefix sum of x. So once you know that, then I can also compute the average of the numbers between x and y. Average of the numbers between x and y, how do you compute this? You first find the sum of numbers between x and y. And you can also, using the rank function, you can also find how many numbers are there between x and y. Divide the sum by the number of elements, you'll find the average. You can also find, let's call this function as more than the average. I give you two pointers, x and y. I want you to find how many numbers are there between x and y, which are bigger than the average of the numbers which are between x and y, right? So how do you find this? You find the average using the previous function, then you find the rank of the average. So the number of numbers which are between x and y, which are bigger than average. So all the numbers which are bigger than average but smaller than y is what I want. So this can be found by finding the rank of y and finding the rank of average of these two numbers. The answer will be the rank of average of x and y minus the rank of y. So that will give you the number of numbers which are between the x and y which are bigger than the average. Right, so average of these two numbers will lie between x and y. So that's some number which is between x and y. Now, if you want a numbers which are greater than the average, so you basically find that, let's call it as a. So you can find the number of numbers which are between the average and y by finding the rank of y minus the rank of the average, which both can be found in order log n. So if you have the basic implementation for the AVL tree, you can do all these things, all these operations in order log n, right? So in this, so this is called augmenting the data structure. We built a AVL tree just to implement search, insert, and delete. But after that, we have added few more parameters to it, augmented with the count. And this example also shows that if you augment with sum and update these extra variables that you're keeping track in order login, when you do the insertion and deletion, you can perform all these operations in order login just by augmenting, keeping track of few more variables. Okay, that's what we learned in this video. In the next few videos, we will see more applications of AVL trees and to solve problems of different kind. Okay, so we'll take a quick break and come back sometimes later to see more applications of AVL tree. Goodbye.